OK， 那我们最后一位哈是那个Dr. Michael, right? Yeah. So you are going to use the English or Chinese? Yeah. It's very difficult for you, right? In Chinese, yeah. OK. 它的题目呢是要进行那个biodegradable plastic from recombinant E. coli to the low cost and sustainable bioplastic. OK, it's your turn, Michael.
Today I'm going to talk about biodegradable plastic from the recombinant E. coli. So first, I would like to introduce myself. My Chinese name is 谢达荣, but you can call me Michael. And I was work as a senior researcher at Avatech company, and I was graduated from Fengshan University, and my expertise is about biogas production, wastewater treatment, biopolymer, and cell immobilization. So today I'm going to talk about the global plastic issues, and the next thing is I'm going to talk about the bioplastic and then a bioplastic research process at Avatech and our future plan. So first, I would like to tell you a story about there was a king who was gifted by the god with the talent of when he touched anything, that object would turn into gold. Firstly, he thinks that is quite a wonderful gift from the god, but actually the thing is he soon realized that is actually the curse, because he cannot eat anything. Anything that he touched would turn to gold, even his food. Even his friend, his family, everybody around him turned to gold. And so we humans also have quite similar gift to the king that I just mentioned. It started from the beginning of the 20th century, at the time that we first invented the plastic. So at the first look, the plastic has a lot of wonderful properties, like it's sterile and it's quite very cheap and really easy to make it, and also it has a quite decent durable. But the thing is, the plastic, one of the property of the plastic that cause a lot of trouble to us is degradable. Yeah, the plastic is degradable for quite a long time. So because for example, under the exposure to the UV light, and the plastic can turn into microplastic, and this microplastic can go up to the food chain and to our ecosystem and into our body. So this causes a lot of nasty problem to our health and also our society and economy. So our solution is to produce some so-called the bioplastic, and the bioplastic can be classified into two categories. The first one is the hydrophilic bioplastic, like a starch-based, cellulose-based, and like the protein-based. And the other one is the hydrophobic bioplastic, which is the main subject of my presentation today, which is the PLA and the PHA. So, at our company, that our purpose is to utilize a low-cost feedstock to use that to grow the bacteria, like some fast-growing bacteria like the E. coli, and we do some tinkering with their genome so they can act as the bioplastic producer. So at Avatech, our key technology is we are developing we're trying to apply the technology which is called the CRISPR. So the CRISPR is quite a very new technology in the genetic modification, genetic manipulation. And for this one, it's a little bit different to the traditional genetic modification technology, in which it can, it can change the intrinsic, it can provide us intrinsic customization of the genome, while the traditional technology, we need to insert the foreign DNA into the cell. And as we know that the foreign DNA, if we insert into the gel, and it will have a very high percentage that it will getting reject from the cell. So CRISPR result in the more stable and cheaper genetic work. So this is the quite basic step for every of the genetic modification work. At first, we need to do gene construction. So gene construction, only 2 words, but this is quite complicated. We can choose some of the DNA, some of the interested gene from any kind of the living things. And first, we need to extract it from the living cell. And then we need to cut it with enzyme or something, and then ligate, which means combine it with another interested gene that we desired. And then after all of the hard work, we need to input the gene construction into the cell with a process called transformation. So before this transformation, we need to prepare the cell, and we need to thawing it from our freezer, and then we need to streak it, and then we need to pre-culture and then culture it. So this takes a lot of time to prepare the cell for the transformation. And after we can get the transformation successfully, then we can incubate the cell and do the spreading and do the pre-culture again, and then go for fermentation in the big reactor. So for the PHA, then we can directly harvest the cell itself and extract the PHA from the cell. For the PLA, we still need to recover the lactic acid from the culture medium, and then we need to do another process called polymerization to achieve the PLA. So as you can see here, obviously the PHA is kind of more natural than the PLA. So this is the demonstration for the lactic acid production genetic strategy. So this is kind of a little bit complicated, but you can see that all of the bacteria, they have to do their things to live, to survive. So they need to have some intermediate product that in this case, for the E. coli, they need to produce something like the succinic acid, the acetic acid, and ethanol for their living. So the point is, in order to produce lactic acid or the PHA for our purpose of plastic industry, we don't need them to live that strong. So actually, that's why we need to delete all the pathway that produce that intermediate product. Like in this case, we can try to use the CRISPR technology to knock out the gene, or knock out means delete, which means there's no more of that gene in that bacteria. So after that, we can get rid of all of the intermediate product like the succinic acid, acetate, and the ethanol. So that is the first step, get rid of all of the intermediate product. So the second step is, like in this case, for the lactic acid production. So we need to get rid of the pathway that the bacteria naturally use to produce the racemic lactic acid. So racemic lactic acid, which means it has 50% of the L form and another 50% of the D form lactic acid. So actually, we don't really like this kind of product. Like it doesn't have the desired property for the later application. So that's why we also need to delete this pathway also. And then, depend on what kind of form, L form or D form, then we can also, like for, in this case, is the strategy for producing the L form lactic acid. And in this case, we can also delete completely the pathway to produce D form lactic acid. And also, we can overexpress the pathway to produce L form lactic acid. And also that lactic acid also can be utilized by the E. coli to do its stuff. So we also need to delete the pathway that the E. coli can utilize our precious L form lactic acid. So that is the very basic step if we want to manipulate the genome of any bacteria or any living thing. And the other thing is, this is the last thing, is like we also need to express the gene if we want is to utilize something very hard to eat, like glycerol. Glycerol actually is for the bacteria. If for the natural one, they don't really they don't utilize it very efficiently. So we still need to overexpress the gene. Like this one is the gene named the GLPK and the GLPD. So it can utilize the glycerol effectively. And this also can be applied into another stuff like maybe like something like agricultural waste. So our other project is to produce the PHA. So PHA is quite new at our company, and I'm certainly working for construct the gene to produce the PHA quite recently, just over for 2 months. So PHA stands for the polyhydroxyl alkanoids. So in nature, this PHA is generated by the bacteria as a kind of the storing energy. It's just like the fat in the human body. So bacteria generate this PHA under some difficult condition, like insufficient of nutrient like the nitrogen, the sulfur, and oxygen. And the PHA has PHA. So PHA has a lot of things like PHA is the general term, and PHB, PHB, PHBV or something is they are all the type of the PHA. So this PHA has quite a similar property to the petroleum-based plastic, and the most important thing is it is biodegradable and is natural, compostable, renewable. So in the E. coli strain, actually E. coli cannot produce the PHA. It doesn't have any function in the E. coli. So that's why if we want to produce something like the PHA inside the E. coli strain, we need to construct the gene outside and then insert that gene into that E. coli that we design. So this have one advantage for the E. coli is normally, as I just mentioned, that the PHA is the storing energy for the bacteria, which means they will they will consume or eat the PHA anytime very soon. But for the E. coli doesn't need to have the PHA. It is not a natural product inside the E. coli. So that's why E. coli don't eat the PHA. So we don't need to worry about losing any PHA inside the E. coli. And the other thing is the E. coli grow very fast, and their genome is very easy to manipulate. And also the cell of the E. coli is very fragile. so which is have advantage when we want to extract the PHA from the cell. So there is some key, this is some general key strategy if we want to enhance the PHA production from the E. coli strain. So one of the first strategy in which we are doing in our lab now is to enhance the PHB accumulation by enhancing the operon called the FAR-CAB, which include 3 genes, the FAR-A, FAR-B, and FAR-C. FAR-A and FAR-B is to generate a precursor for the PHA, and for the FAR-C is to synthesize the PHA inside the cell. So the other strategy that we think about is to change the growing pattern of the cell. Like instead of one cell, instead of one cell divided into 2 cells, we can make it divided into more than 2. And also another strategy is to enlarge the size of the cell. And if we enlarge it, and it is easier to collect the cell, and it's easier to break the cell. So this is the quite fundamental strategy, genetic strategy for enhancing the accumulation, PHA accumulation inside the E. coli. So like for example, this one, first, we need to enhance the glycerol utilization. So our first experiment is to use the glycerol to grow the E. coli so they can accumulate PHA inside them. And then follow all of the steps here to acetyl-CoA, and we need the gene of FAR-A to produce the acetyl-CoA, and the FAR-B and go to the FAR-C to have for the E. coli to accumulate the PHA inside them. So actually for the PHB and the PLA, that we have a lot of application for them. But this one is the most, I think it's the most common application that we can think about so they can replace the petroleum-based plastic. Like the first thing is they can replace the conventional plastic from making tableware, like a straw or for drinking water or something. Because every morning, you know, since the day that Taiwan banned the use of the straw in a convenience store, then I don't have any straw to drink water. The other thing is like bottle drawing bags, and of course like at Evertech we produce seals, labels, and glue adhesive substance. So our future plan at Evertech for the PHA and the PLA, actually for the PLA we already have the full-scale production, but for the PHA we just started with it, and so therefore our first step is to have the PHA producing strain first, and then we will try to think about how to improve our extraction process and also the purification process for this bioplastic. And also we try to develop inserting any kind of gene to improve, so to let the E. coli to have the capability to utilize all the many kind of low-cost feedstock. So that's it for my presentation today. Thank you for your attention.